Ladies and gentlemen, the floor is yours. What questions do you have? Arc length, surface areas of revolution, or applications for center of mass? And in all of the running around, I did both forget the boomerang and the yo-yo in my office again. There's center of mass application hand of a knife, and that's not a good thing to play with in class. Yes, sir.
2 on 8.2.
8.2, number 2. So we want to set up the integral to go around either axis, right? So let's start with the first question. If I'm going around the x-axis, what's the integral in question? Yeah.
Pi times x times square root of 1 plus the derivative of the function squared.
Two pi x. Let's think about this. If I'm going around the curve this way, right, then I can think of the surface area of this like it was a cylinder, 2 pi radius times the length of the side. Well, the length of the side is the ds part. Is the radius of this an x or a y? So it's 2 pi y ds. Now, that's when I'm going around the x-axis. If I'm going around the y-axis, then my circle will be oriented horizontally, right? My cylinder will have its side, then the radius is going to be an x value. Now, in our case, the equation is given to us in terms of x. So regardless of which of these I'm doing, I think I'm better off writing everything in terms of x. So there, my ds is that arc length differential piece, right? The square root 1 plus f prime squared. So now I just have to work out what that is. And then I'll be able to put those in here. And here I'll put this. Here I'll just leave it as an x. Now it does say in part B not to do these integrals by hand, but to use the numerical integration capability of our calculator, right? So once I get all the integrals set up, I can do them directly on here using the integration capability there.
That actually might be where I messed up. I don't know if I read that.
Yeah, I was going to say, we don't want to do these integrals because they suck so badly. I mean, one of them is just, it's an atrocious substitution. The other one is even less so pleasant. Yeah, we don't have to do either of these integrals by hand. And it wants it to 4 decimal places. So once you've got it set up, plug it in here and write it down to 4 decimals. You can also do it on Wolfram Alpha if you want, but this is something you'll have with you when the exam time runs, so it pays to know how to do it on here. Yes, ma'am. This one is rotated around the x-axis. This one is rotated around the y-axis. Because remember, it's where is the radius of our rotation. In the one on the left, we're going this way, so the radius is horizontal. That's why the r is an x. And then over there, it's vertical, so our radius is a y. You're welcome. Which is why I tend to draw those stupid little swirly arrows or really bad looking circles as to what I'm actually trying to rotate. More questions? Yes, Leo.
Number 8.
Number 8. Now this one it does want us to do. Y equals root of 5 minus x and its x is between 3 and 5. And we're rotating around the x-axis. If we're going around the x-axis, okay, Nora, here's why. I'm going to use the vertical rotation. The radius of that circle is a vertical segment. But because I'm that sort of person, the graph of this is a backwards parabola. It's a square root. And we're only going to 3. So there's my circle of rotation and the radius of that circle, the y value. But everything within this equation is going to be written in terms of x. Because all of these pieces are given in x, and I'm pretty sure it's going to be easier to work out the integral if I do that. Leo, we good so far? So, a and b are the limits of my integral. So I'm going to go from 3 to 5. 2 pi, y is this equation. I need dy dx. I haven't worked that out yet, so let's go over here. What's the derivative?
It would be like 1/2 times 5 minus a negative half times -1.
Power rule and chain rule. Great. Remember, I've got to square that. Oh, and way down here on the end, there should be a dx, but I've run literally up against the edge of the paper, so I'll just put it out there for the moment. I am hoping right now, Dom, that I am going to end up with something I can actually do, which means I'm hoping for an algebra nightmare to resolve itself. So let's do some algebra. Leo, talk to me. What do I do?
So I have this negative
squared, minus 1 over 2, it would be 5 times squared. So it would be like 1 over 4 times 5 minus x. It'd be 1 plus that.
Like that?
Then you get common denominator.
Before I do that, there's one more thing you've made a slight, this is not quite right. There's something either I didn't write down or you didn't say.
Negative.
There's a -1 power here because I've squared the -1/2. Means I've multiplied powers together. If it's a negative power, it goes in the bottom. Keep talking to me, Leo. You said something about a common denominator.
1 over 4 times 5 x. So you need to say 1 multiply that by 5 minus x plus 5 x, would be 4 times 5 minus x over 4 times 5 times x.
Which makes this top 20 minus 4x plus 1. Or 19 minus 4x? No, 21 minus 4x. Why am I happy to see that? Square root of the top, square root of 21 minus 4x, but on the bottom, what do I get? And then the square root of 5 minus x out front, it'll cancel with the 1 on the bottom. But wait, even more cancels. What else cancels? Exactly. The 2 from the 2 pi out front and the 2 in the denominator. Leo, what do I do now?
How did, so you could cancel out those 2 square roots of 5 minus x and the 1 is inside it. So it would be over 4 of this.
Right, but over 4 is it's the square root of 4.
2.
And then there's a 2 out front.
2 pi, that makes it pi.
So now I'm left with a u substitution. Yay, I can do this one. So Leo, I'm going to stop here. You can do the u substitution and finish this one out, okay? All right. More questions? Nora, you're glaring at the problem, me, or the book? Okay. So how can I help reduce that glare? 8.122. This one? Okay. Ew. I'm going to start by asking a really dumb question. What's this look like? What's the graph of this? Now, the problem is that I can't graph that in my calculator the way it's written. So either I have to rewrite it to write it as y equals, which is going to require a cube root, or I'm going to need to graph it in something like Wolfram Alpha or some other graphing app like Desmos. You have a preference? Let me make my life easy then. Use my quick grapher. These are bright over here. Not going to work very well. I got to turn the light out so you can see this. Hey, look at that graph. Now I'll just type the equation in exactly as it's written. Clear. X to the second equals parentheses y minus 4. Minus 4. Close the parentheses. Raise it to the third. Done. Aha! This kind of looks like a kid's drawing of a bird, right? I'm going from the point 1, 5 to the point 8, 8. Now we turn all the lights back on. Now you have your choice. We could do this integral in terms of x or in terms of y. Because we want the arc length, we could either do that like this, or like this. And it's literally your call. I think what's going to make the difference is which of those derivative expressions is nicer. Which means I should go back to the equation, I should try and write it y equals, I should try and write it x equals. And I should see which one I like. All right, so if I take this expression, I can write it x is the square root of y minus 4 cubed, which is the same as y minus 4 to the 3 halves. Now that doesn't suck. Or I could take the cube root first, and then I could move the 4 over. So if I want to do it as f of x, this is f of x. If I want to do it as g of y, this is g of y. Ready? I want the derivatives of each of those. I want f prime of x. I think you subtracted incorrectly. You take this power, you bring it down. Over there, I have the 2/3 on the other one. If I think of this as g of y, then g prime of y is 2/3 x to the 2/3 x to the negative 1/3. I've now said that exactly backwards. This is g of y. This is f of x. It helps if you read which freaking variable you're working in. I apologize. That was dumb of me. So, I need to square that and then put it inside a square root and then do this integral, right? Which of those will be nicer when you square it? The first one on the left or the second one on the right? Because this has a square root, and when I square it, the square root will go away. This one has a negative 1/3. When I square it, it'll be negative 2/3. That's nasty. I think I want to work with this one. So that means I'm going to do my integral like this. Question for you. What numbers should go on that integral? Go back to the picture. Exactly, the y values of the 2 points. So I can take that, I can put it in here. What do you get inside the square root? I bet if you multiply that out, that's just a linear thing in y, right? That's a u substitution. It's gonna work.
So I got like the square root, 9/4. I want to take it because like the minus 9 plus the 1 minus.
With the 4, right? Yeah, when you multiply through, absolutely. 9/4 y minus 9 plus 1. Yeah, that's going to be a nice, easy square root to deal with. Yay. Look, you're less angry with it. I like this. This is good. See how I had to go through and decide which way was going to be the right way to do this. When I'm doing the rotations, there's a clear benefit to using one formula over the other, depending on the direction of rotation. But in this case, I think there's another problem that we do in this section that uses the same equation. It asks you to do it in 3 different pieces, but that might be later. Might actually be in a different section. So because I can't seem to find it off the top of my head. But is that better? Wonderful. Jacob, you had a question for me too. 34 of 8.1. I think this is the same setup, because what's the equation in that problem? Aha! 1 cubed, the other one squared. This is the same setup as the one we were just dealing. They just got rid of the -4. So you're asked to set up the integral that goes from 1 I'm sorry, from 0, 0 to 1, 1. Now again, they want a picture, right? Well, this one I can actually write in my calculator fairly easy, so I can draw that one on the calculator. It asks me to do this two ways though, right? It says, observe that one of the integrals is improper. I can write the equation this way. I can also write the equation that way. When I do the derivative, I get a negative 1/3 there, right? But when I do the derivative over here, I have a positive power still, right? This negative power is undefined at 0. So when I do the integral in x, when I go to plug in 0, 0, I'm going to have to use the limit. That's the setup in this problem. Other than that, it's basically this problem again. There's a sneaky thing, I think, in part to go from -1, 1 to 5 to something else. Part C, -1, 1 to 8, 4. But notice this piece right here. That's the integral you're doing right here, isn't it? And this piece is the same length, just flipped the other way, isn't it? So once you know this answer, you don't have to do that. You can do part 1, part 2, and part 3. But you already know the numbers for these. You just have to work out this one. Now, mind you, that's a total of 3 different integrals. We have to do 2 integrals up here, and then we have to do this one here. So whatever length you work out up here, that's the length of this little piece on this side and this bolded piece here. But then you also have to work out this length separately. More questions, ask me more things. Fourteen. ln of cosine of x. From where to where? 0 to pi over 3. Since they've given me the bounds in x, I'm probably going to be better off doing this entire problem in x. So I think my arc length should go like this. $1,000 question, what goes in the parentheses? Even better. Because it's 1 over cosine times the derivative of cosine, which is minus sine, so minus tangent of x. Beautiful, wonderful, brilliant. You're squaring that, yes? What happens to the minus? I've seen that before. What does that simplify to? That is one of my Pythagorean identities. That's one of those trig things that we were doing in the chapter on trig integrals. You remember it? Okay, so that's all I can give you too. I vaguely remember it. So what I do every time is I start with sine squared plus cosine squared equals 1. I want tangent, right? Tangent is sine over cosine. So we divide by cosines. Cosine squared, cosine squared, cosine squared. This is tangent squared plus 1 equals secant squared. So what's under that square root is a square root of a secant squared. And the integral of secant, because the square and the square root will cancel each other out, is on my formula sheet. Wait, I need to do Renfield. It works. It works. Sorry, that's Igor. Renfield eats the flies. Igor does not. Wrong monster movie. More questions. Yes, sir.
8.346.
8.346. Use the theorem of Pappus to find the volume of the solid obtained by rotating a triangle with the given vertices around the x-axis. Okay. What are the vertices in question?
2, 3, 2, 5, 5, 4.
My crappy looking picture here. So far, so good? You're going to rotate this around the x-axis. What does the theorem of Pappus tell me?
That if the region is rotated about the volume of the resulting solid is the product of the area of the region. The center of it.
I'm going to cheat so hard your eyes are going to pop out of your head. You need no calculus to do this problem. Okay, wait a minute. I promise I'm not with you. You can do this without any calculus at all. What do you know about that triangle geometrically?
What are you looking for here?
Whatever geometry ideas you can think of about triangles, do they apply here? The two sides are the same length, right? The top diagonal side and the bottom diagonal side are exactly the same length. The word you're looking for is isosceles. Isosceles triangle I need to know where its center of mass is, right? Where's the balance point? But since I'm going around the x-axis, I don't care where it is left to right. I only care where it is up and down. An isosceles triangle, there's some symmetry involved. Right down the middle, I should be able to fold this sucker top to bottom perfectly in half, right? And that means the centroid of this triangle is somewhere along that middle line, isn't it? Somewhere along this line is the centroid. I think it's going to be closer to the left than it is to the right, but I don't care about that much. Let's just put it somewhere on that line. What do you know about the coordinates of that point? Can you find the area of that triangle? 1/2 base times height, right? Now, think about what you're going to do. You're going to spin this sucker. That point is going to move in what shape?
Circle.
What is the distance that point will travel when it goes around that circle? No, it'll start and end in the same spot. The displacement will be 0, but it will have moved how far? 2 pi r. What's the radius of that circle? Say it again. The circumference of the circle, whose radius you figured out, times the area of that triangle. I didn't do a damn bit of calculus, but I did a crap ton of geometry, didn't I? I would love to tell you that you never have to remember all this stuff you did before, but we keep using it everywhere. Tom, better?
Yeah.
This is one of those questions that is thrown into this sort of section because you think about doing the calculus here. That's really, really hard. Finding the actual shape, you'd have to find the equation of both lines. You'd have to use the method of washers to do that. Ugh, I don't want to do that. That's disgusting. It's doable, but it's going to suck. Calculus theorem is so much easier. More questions. Ten on 8.1. 36y squared equals x squared minus 4 cubed. We're in the same square and cube thing again a lot, aren't we? 36y squared equals x squared minus 4 cubed. This was 10, you said? 10. No doubt. There we go. I think I'm going to do the same thing I did in the previous one, because it says we're going from 2 to 3 and y is bigger than 0. And I'm going to take a square root. What's square root of 36 minus 36y squared?
36y.
Poof. And over here, I get x squared minus 4 to the 3 halves. I'll move the 1/6 over and I'll be able to write y equals 1/6 x squared minus 4 to the 3 halves. And again, I'll wager some really nice stuff happens when I start looking at the equation I need to deal with to the arc length, right? We're going around which axis? I'm going around the x-axis. The radius of my little circle is a y value. So I use 2 pi y ds. So I'm going to get the integral. Oh, wait a minute. Before I do this integral, I need y prime. That would be my f prime of x. What's the derivative of this thing? I don't know where you got the 9 from. I'm supposed to take this down and multiply, right? I'm okay with that, 2x, but what goes up here? So what happens here? Setting up for slides that starts with 2. Damn, so what happens out front is that I get a 4th. But then there's that other 2 on the end, so that's going to turn it into a 1/2 x squared minus 4 to the 1/2, and then just an x here. So far, so good? That's what's got to get squared. There's a lot more messy algebra coming up, isn't there? What happens inside when I do all of that algebra inside the square root? Oh, stop. That's the surface area integral. I just want the arc length. There's no 2 pi y, there's just the ds. My apologies. Hopefully the algebra now is a lot nicer. It's not great, but it's nicer. Let's see what happens. I multiply this out, and I get 1/4 x squared minus 4 to the 1, and then I get another x squared. Right? So all of that is over 4. So instead of writing 1, I'll write 4 over 4. Yes? And now I see x to the 4th minus 4x squared plus 4 over 4, and I have an algebra's wonderful, wonderful, wonderful occurrence. Squared. What's the square root of that? Jacob? And now there's no more square root to deal with in my integral. Thank you, Lord. Better. Sometimes it's not the calculus. The integral is going to be easy now. It was getting there. All right, ladies and gentlemen, I will see you all tomorrow morning, and we will turn this in and we will do more applications in other directions. And if you've got other questions, I'm going over to the Enrichment Center right now to do my office hours. Send me emails, however you want to deal with it. Thank you all very much.